Welcome back to the next lecture in this series on programming languages. Today we're going to have a deeper look at the story of types and subtypes and classes and subclasses and what their relationships exactly are in object-oriented programming languages. The lecture today is split up into two parts. First, we're going to have a closer look at objects and type compatibility. And in the second part, we're going to have a deeper look at subtyping and what exactly is the relationship between subtyping and subclasses. Here's a bunch of questions that are somehow existential that you may not have considered in some detail, but these are the topics that we're going to try and hit today. We want to try and understand better exactly what an object is anyway, and how can we think of an object in a more formal fashion. Second of all, what exactly is meant by type? We've been using types in programming languages for some time, but we haven't considered deeply what do we mean by a type and whether there's a notion of a type which covers different kinds of programming languages. We've seen in object-oriented languages the notion of a subtype, but what exactly is meant by a subtype and what's the relationship between types and classes anyway? In languages like Java and C++, we know that there's supposed to be a correspondence between inheritance and subtyping, and the inheritance relationships are used to establish a subtype relationship, but are they really the same thing? And when exactly is a subclass also a subtype? Is it always the case that this makes sense, or is there something different going on? Because if they are the same thing, why are we using different terms? First of all, let's have a look at the story of objects and type compatibility. I'm using a variety of sources for this lecture today. The key one is the one listed at the bottom. This is a classic tutorial survey by Anthony Simons dating from the early 2000s, published in the Journal of Object Technology. I highly recommend you to use this as a backup source, and I'll be using his lecture notes for the lecture today. Also for this first part, there are several classic articles that I'll be referring to. One is an article by Lalonde and Pugh, which discuss the relationship between subclassing, subtyping, and ISA, that dates from 1991. Then there's also a classic article by Wegner and Sedonic looking at the relationship between inheritance and how it's used for incremental modification. And finally, there's also a classic article by Listkov and Wing on a behavioral notion of subtyping, and we'll touch on all of these. First of all, I want to have a closer look at what is meant by substitutability. So when can one object be substituted for another? Starting from the article by Lalonde and Pugh, they have a very interesting discussion of the relationship between subclassing, subtyping, and ISA, and how these are actually different things. So if you look at a collection hierarchy, there's one notion of subclassing, which is that which focuses on reuse or incremental modification. So here the class collection inherits from object and adds some features. Private hash array is a kind of collection which adds some additional features, and a set is implemented internally as a private hash array and inherits from private hash array. We can certainly do that. And a bag is kind of like a set, but with some slightly different implementation details, so we simply inherit a bag from set and make the changes in the subclass. So this is using inheritance hierarchy purely for reuse and incremental modification. So this is just subclassing at its most rudimentary level. Next, there's a notion of subtyping, which imposes a strict notion of substitutability. So when I say something is a subtype of another, that means that when I declare a variable or an argument to be of a particular type and a substitute for it an instance of a subtype, then I should get no errors. So everything should work, whatever that means. We'll go more deeply into that in the rest of this lecture. So for example, if I'm expecting a collection and I provide a bag or provide a set or provide an integer set, then all of these should work. They shouldn't raise any type errors. Finally, there's the notion of specialization, or ISA. So this means that a particular class is a more specialized form of another one. So a collection specializes an object, and a bag is a special kind of collection. A set is a special kind of bag where each element can appear only once instead of multiple times. And an integer set is a more specialist kind of set that only contains integers. So this is the ISA relationship. These three are orthogonal in the sense that you can have any one of these without the other two, as we see in this hierarchies here. Wegener and Stonick a few years earlier also introduced the notion of substitutability in their classic ECOOP 1988 paper, Inheritance as an Incremental Modification Mechanism, or What Like Is and Isn't Like. They state that an instance of a subtype can always be used in any context in which an instance of a supertype was expected. This sounds like it makes sense, but what does this actually mean? What is meant by a context, and what is meant by expected? Does it mean that no errors are raised, or what kind of errors? Just interface errors or other more deep semantic errors? It's not entirely clear. So depending on what you choose or how you interpret these terms, you will get different forms of subtyping. Now, let's consider what we mean by compatibility. In the survey articles by Anthony Simons, he speaks of, he starts by considering what is meant by component and what it means for a component to satisfy the expectations of a client. So a client has a component and has some kind of expectations, and this is what is expressed by a type. So a supplier provides a component that should satisfy these expectations, and a compatible component provides what the client requires. So there's some kind of specification of these expectations, and that defines what it means for things to be plug compatible. So it's the plug compatibility, which is this fuzzy notion that we want to try and pin down. And you have different levels of compatibility, but very coarsely we can distinguish at least two. One is syntactic compatibility. So if you're syntactically compatible, the plug, you satisfy the interface, the plug just says, well, you should have operations with these names and the following signatures. They should expect these arguments and so on, and anything that you pass in should also satisfy this interface, and the thing that you return also has this interface with the following named things. So it all has to do with names. At another level is you go deeper and you consider semantic compatibility. So how do the things actually behave? And here, for example, I could have two components. One is a stack and one is a queue, and they could have exactly the same interface to add things to them and remove things and find out how many elements are there, except there's a fundamental difference. When I add things to a queue, they start at the top, and when I remove them, they come from the back, and when I put things on the stack, they go in the top, and I remove things also from the top. So even though syntactically the stack and the queue might have the same interface, I could define them that way, semantically they behave quite differently. Now the question is, do I want in my type system to capture that or not? So to what depth do you want to capture semantics in your type system? And there are lots of different opinions on these. Moving ahead a couple of years, there's a classic paper by Liskov and Wing, And in this paper, they have the following statement. So they introduced the notion of what is now known as the Liskov substitutability principle. They say, let Q be a property that you can prove about objects of type T. Then if I have an object Y of type S, where S is supposed to be a subtype, then that same property should go for instances of the subtype. Notice this doesn't say what a type is or exactly what substitutability is. It depends on what the properties are. So the key issue is, what do we mean by Q of X here? So Q of X is a property, but what properties are we interested in? Let's have a look. Next, types and polymorphism. Before we can have a deeper look at types, let's roll back a little bit and review some terminology that we've seen in the previous lectures. First of all, static typing. We can, the static type of an entity is the type that we can reason about based on the source code alone. So language is statically typed if you have a type checker that checks based on source code. Dynamic typing ignores the source code and looks at just at what happens at runtime. So then only values have fixed type. So we're not interested only in the variables, but just the values of expressions. So values have fixed type. There's this term strong typing, which I discourage. It just says that it's impossible to perform an operation on the wrong type of object. But by those terms, both static and dynamically typed languages are strongly typed. Very often there's a confusion between strong typing and static typing, so they're not the same thing. You can also have a statically typed language which is not strongly typed, so older versions of C were statically typed, but the type guarantees were rather weak, so you could still get type errors. So static typing and strong typing are not necessarily the same thing. How do you do the type checking? Well, there are different levels. You can do compile time type checking based on all the declarations in your source code. You can do compile time type inference, as we have seen in Haskell, which relies partly on type declarations and partly on what the type checker infers types to be. Or you can do everything dynamically at runtime, and as you have in dynamic languages like JavaScript or Smalltalk. We also speak of polymorphism. Polymorphism is more easily understood in contrast to monomorphism. So in a monomorphic language, everything has exactly one type. So in a language like C or Pascal, these languages are monomorphic. Essentially, there's no notion of subtyping. With a polymorphic language, variables may hold values of various types. And then there are different forms of polymorphism. So all object-oriented languages are polymorphic. Simons points out, beware of object-oriented textbooks. Very often the authors confuse what polymorphism is, and they refer to dynamic dispatching, dynamic behavior of objects. That's completely wrong. Polymorphism does not refer to anything to do with dynamic behavior. It refers to the fact that variables may hold values of more than one type. This has nothing to do with static or dynamic binding, so this is a complete confusion. Once again, review. We speak of polymorphism, but there are many kinds. There's universal and ad hoc polymorphism. With universal polymorphism, typically you can define one function or one method, and it's polymorphic. It will take arguments of different types. Ad hoc polymorphism syntactically looks like polymorphism, but it's actually a hack. So in particular, you have overloading. So overloading, you have multiple implementations of an operator like plus. Just because it's a hack doesn't mean it's not useful. But it's not universal in the sense that you have multiple implementations. So you can have overloaded operators, and you can also have coercion. So coercion implicitly converts things to be of the right type. With universal polymorphism, on the other hand, you have one implementation and it's polymorphic. That is, it will take arguments of different types. So with parametric polymorphism, like you have with polymorphic functions in Haskell or with generics in Java, you have methods that will take arguments that are of multiple types. With subtyping or inclusion polymorphism, on the other hand, you're relying on the subtyping hierarchy as you have in object-oriented languages. So that's what we'll mostly be focusing on in this lecture. So we're not interested so much in parametric polymorphism, overloading, and coercion. We're mainly interested in understanding subtyping and its relationship to subclassing. Now, back to type compatibility and what we mean by type compatibility. There are essentially roughly 3 different categories of compatibility. The first is exact correspondence, and this is what we see in monomorphic languages. The component has exactly the right type, so it's matched 1-to-1. I expect something of type string and I get exactly a string. No subtypes, no subclasses, no nothing. So just exact matching. Then we have a notion of subtyping. So the component is of a more specific type, but behaves exactly like the more general one. And then there is subclassing. So subclassing is like subtyping, but instead of just being exactly type compatible. So think in subtyping we specify an interface, like in Java, and we can have multiple classes that implement that interface. That's a form of subtyping. With subclassing, I declare something to be of a particular type, which corresponds to a class, and then I'll have a subclass, which does everything that the superclass did, but more. So it somehow extends the type. So this is a different thing that's going on. And subtyping and subclassing are somehow, there's something going on which we need to understand better. Now, on the one hand, we have different kinds of compatibility, and on the other hand, we have different ways of thinking about types. At the lowest level, we have a bit interpretation schema. So these are memory storage requirements. This is essentially what you have in old-style C programs. So for things to be type compatible, the representations have to match. So we're not so much interested in interfaces because we don't have data abstractions. We just have a type is a bunch of bits that fits a particular kind of a template. So I can even convert something that's of one type to another if the bits match up. Next, we have so-called model-based and constructive types. Here we view types as sets of values. We'll see a little bit of that as we move ahead. Then, at the next level, we have syntactic and existential abstract types. So here, types are sets of function signatures. This is much more close to what we are used to in object-oriented languages. So basically, a type is kind of a data abstraction. And finally, the most advanced kind of types, we think of types not just as signatures, but also some axioms. So we consider also some behavioral aspects. For example, you can define stacks and queues as algebraic data types, and you can perform reason about operators over these entities. Most of our focus in this lecture will be on the third kind, so types as sets of function signatures, but we'll be bumping into some of the other kinds as well as we move along. So this is the kind which most closely matches what we think about when we're thinking about objects, types, classes, subtypes, and subclasses. In order to proceed, we need to have some way of thinking about how to express type rules. So I'm going to introduce you to a standard way of describing the static semantics of such languages. Here we see again the different kinds of typing and different kinds of types that we have arranged as a grid. And this will help us to compare different kinds of languages. So there are languages which consider type checking in terms of exact type matching, languages which focus on subtyping, and those that focus more on subclassing. And there are languages that are based on bit schemas, on interfaces, and on algebras. So we simplified a little bit what we've seen before in the last two slides. So as concrete examples, if you have a language like C, C considers types to match if they're exactly the same, and it's at a low level representation, essentially the bits. C++, on the other hand, also requires objects to match the bit schemas, but it has a notion of subtyping, which is very important. Moving along to interfaces, languages like Pascal and Ada, they also have a notion of types of interfaces, and also C supports that as well, but they're monomorphic, so we have exact matching. Moving on to object-oriented languages, we also have a notion of subtyping based on interfaces, as we see in C++, but also in Java and some other languages. Finally, there are languages like Smalltalk and Eiffel, which are focused more on subclassing than on subtyping. And then there are languages like OBJ, which support an algebraic notion of types. Mostly we're interested in the square right at the center. But let's do a quick survey of the different kinds of languages. So we'll see different parts of this grid. So if we want to type check exact interfaces, then we start with some sets corresponding to primitive types in our universe, entities or values that are elements of these sets. So little a is a member of the set big A, and so on. We have set operations, such as membership of a set or subsetting inclusions. And we have some logical operations. So to warm up, let's have a look at what the type rules would look like. Now, here we see a classical example of a type rule. So this is pretty standard in the definition of the static semantics of programming languages. So when you define a programming language formally, you have two parts of the semantics typically. You have the static semantics and the dynamic semantics. The static semantics essentially expresses the type rules, so it tells you which programs are valid. That makes sense, so performing typically kind of type checking, but also scoping rules. And then there's the dynamic semantics, and it tells you what happens when you run a program at runtime. So as we saw in the lambda calculus, you can have there aren't any interesting type rules, but you do have the dynamic semantics that tells you with the alpha, beta, and eta rules how to evaluate lambda expressions. We also saw very, very briefly the example of featherweight Java, which had both static and dynamic semantics expressed as rules. Let's see a bunch of examples here of these type rules and how to read them. So they're actually pretty straightforward to read, but you have to get used to the notation. So here, what these rules look like, there's also always a line, and the part that's above the line, these are your preconditions, and what's below the line is what you can conclude. So here, if we say if n is of type big N and m is of type big M, then the tuple nm is of the type the cross product n times m. So this is, the rule looks a little bit funny if you've never seen them before, but they're actually pretty straightforward to read. So this introduces a product. So these are, if I have two types n and m, then I can create a product type n times m. So this will allow me to create tuples, or pairs in this case. Let's go on to some more rules. They're also pretty easy to understand once you get used to the notation. Here I say if I have a value e, or an expression of type n times m, so it's a tuple, so e is a tuple, then I have the operators pi1 and pi2, and they extract the first or the second element from the tuple. Then if I extract the first element from e, it's going to be of type n. And if I extract the second element, it's going to be of type m. So as you can see, the rule looks a bit funny, but once you are used to how to read it, it's not saying all that much. It's just saying in a very formal way what we mean by these types. So far so good. Now let's look at function introduction. Here we see an additional thing called a turnstile. It allows us to introduce an implication in the precondition. So if given some variable x of type d, we can conclude that e is of type c, then lambda x dot e is going to be of type d arrow c. That means that this x may appear somewhere in this x. So given the information that x is of type d, if that allows us to conclude this, then the function obviously is going to take a lambda of type d, and it'll return an e of type c. So the type is d arrow c. Looks again a little bit funny, but once you're used to what this means, in a very compact way, it's telling you what the type of a function is. Next, we have function elimination. Once again, if I have a function f of type f arrow c, function f of type d arrow c, and I have a value v of type d, then f applied to v is going to be of type c. Again, it looks a little bit funny, but once you're used to reading these, it's extremely straightforward. This one looks terrible, but it's really very, very simple as well. The A's the A is a set of labels, so the alphas are labels, and the E's are expressions of some types T. This is just a notation for a record, so a record with a bunch of labels. So I use curly braces, and the alpha 1 through alpha n are just a bunch of labels. So they could be name, address, salary, and so on. And each of the E's are the values. So here I have label name, arrow, E1 is going to be a string. And what's the type of this whole thing? So alpha 1 is of type string, alpha n is of type address or whatever, and all of these are types. So basically all this is saying, if each of these alpha i's is a label and each of these expressions is of some type t, ei is of type ti for I going up from 1 to n, then this value here is a record of type, and here I have curly braces, similar notation, just like we have in Haskell. The expressions and the types have similar but different syntax. So here, instead of arrows, I have colons, and instead of expressions, I have types. So that would mean that name, arrow, some string is going to be name, colon, the type string, and so on. So it just says what's the type of a record. Next, we have record elimination. It's similar. It says if we have an E of type blot, label type, label type, label type, label type. So this is a value, a particular record. Then I can pull out of that record one particular value with a given label, and its type is going to be of type TI. So you can see it's a little bit like Haskell. For every type you have a way of constructing the type and another way of using it or taking it apart. Okay, now what can we do with this? Suppose we want to have a constructor for a point. So what is a point? The constructor is going to take two values, which are going to be our x and a y value. So it's going to be a lambda, so it's a function, and it's going to return a record, okay, in curly braces. And the record's going to have an X component and a Y component. The X component is going to be the first value in the tuple E, and the Y component is going to be the second component in the tuple E. And finally, there's going to be a method called equals. And that method is going to be a lambda, which takes as an argument an instance of the type point. Not of the type tuple, the type point. That's going to be the type of this guy, right? And how does the equality method work? Well, the equality method is going to see if my x value is the same as the x value of my argument, and my y value is going to be the same as the y value of my argument. So far so good. That looks good. But we're still missing something. So, in particular, what we would like to be able to derive is that makePoint is a function that takes a tuple of integers and returns an instance of the point class. When we take all of our type rules, we would like to be able to infer when I have a particular integer that in the end, and I have all of these rules about integers and points and so on, I would like to infer in the end that a makePoint is of type integer times integer to point. That would be nice. However, there is a problem. What exactly is the type point? It doesn't say anywhere here. We don't have a rule yet to reason about classes. Okay, before we can dive further into the story of types and classes, we need to understand better what the heck is an object. Now, there are three possible ways of thinking of objects, or at least three. One is as an existential object encoding. So object is a kind of data abstraction. Second, a functional object encoding. As we'll see, this allows us to think of objects as functional closures, somewhat like we saw in JavaScript. We'll see that in some more detail in a moment. And finally, this is perhaps the hairiest, is using a variant of the lambda calculus, the so-called object calculus, where we can think of objects as self-bound records. And this has to deal with the problem of recursion, because when I have objects, typically in the methods of an object, we also refer to methods that refer to instances of the same class, and that's where all the problems come from. Okay, so the first one, this one looks kind of nice. Let's see what this means. What's a point? A point is a record which has an x and a y that returns an integer and an equality method that returns a boolean. And these things work with some representation, which is part of the implementation of the point, but the part we're interested in is the record. And we don't know what this representation is. It exists. That's why we say it's an existential object encoding. We say point is, there is some representation and we don't care what that representation is, but once we have that representation, we can have an x and a y, which are getters that will give us the integer back. They'll pull them out of the representation. And there's an equality method, which will take the representations of 2 points and tell us whether they're equal. Here's an existential point. So this existential point has a representation. That representation, internal representation, is simply a tuple. So that's the internal representation. It's hidden from the outside. The part that we're interested in to see, so whenever we have an object really in a programming language, there always is a representation, but we never look at it, we never touch it. We always go through the interface. And here, the x, the getter, simply pulls the 2 from the tuple, and the y is also a lambda, so it's a method, and it pulls the 3 from the tuple. And the equality guy takes 2 representations and it compares the first and the second values of the representation to see whether this thing is equal. Sounds pretty reasonable. Looks like we could work with that. So, positive side, it models private state. We don't need recursive types. It's cool. On the other hand, it's a little bit clumsy. All of these projections to extract stuff from internal representations and also to invoke methods is kind of clumsy. And it doesn't model mutation. But maybe we can handle that somehow later. So that's the first way of representing objects. It's pretty straightforward. Now this is second representation. And this is the functional object encoding. Here we say that a point is a record of methods, some of which manipulate point objects. So this is mu. We saw it before. We had this rule here when we were looking at the lambda calculus. Mu just binds a function to some implementation where that implementation may recursively use this f. And we have this rule that allows us to replace the definition for f in the body. Okay, that was this rule here. And it's known by other terms like let recursive or def. These are all the same thing. So we know this from programming languages. It's basically saying, I define point to be this, where point may use itself in its own definition. Well, that's pretty cool. Here's a functional point. I let the x value equal 2 and the y value equal 3 in this record. So this is a recursive let. And here x is bound to the x value, y to the y value, and the equals guy is a lambda, which will compare my x value to my argument's x value, and so on. So essentially, what is this? This is a closure, right? This is pretty much what we had in JavaScript. So in JavaScript, when we could construct a similar point object where the x and y values are part of the closure, they're not part of the record that's returned. It's exactly the view of objects that we have in JavaScript. Now, how do we deal with recursion? That requires an extra recursive step here with our mu operator, because how do we deal with self? So self is a recursive definition here. So here we take the fixed point of self. Self is this whole record. And we want to be able to use self within its own definition. So here we have, again, a functional closure, but we have this extra bit of that shows us how self can be defined as a fixed point. So far, so good. This is the second approach. It models private state fairly nicely. We directly interpret methods. On the negative side, we need this extra mechanism of fixed points, and we're still not modeling mutation. The last thing I'm just going to show you quickly, I don't want to go into the details, just to show you that there is another approach. But it also has some limitations. So Abadi and Cardelli, this is the same Cardelli that of the classic paper by Wegener and Cardelli on polymorphism. They invested a lot of effort into defining various object calculi. This is in the mid to late 1990s. And the idea was to define something like a lambda calculus, but to define it, to use it to define what objects are and object types as well. And they introduced a particular special operator called sigma, and the sigma is the operator that does the recursive, it gives you the recursive fixed point of self in objects. Here's just a very simple example. So here we have a point, and the point is a record, and the record has the X, Y, and equal slots. But the key thing is that in the calculus I have a mechanism for self-binding the definition of self, and all of the semantics is then achieved by the operational rules. So you have the equivalent of beta and eta reductions and so on, but defined for the object calculus. We're not going to look at this in any further detail. I just wanted to point out to you that there is this third path, but it leads to a lot more formal complications than we want to get to in this lecture. So we'll focus on the other two approaches. Now we go into the second part, now that we have some understanding of what compatibility is, or how we can reason about it, how we can talk about types and type rules, and a bit of an understanding of how we might understand what objects are. Let's now look at the relationship between objects and subtyping, and in particular subclassing. Once again, I'm referring to the tutorial survey by Tony Simons on theory of classification, parts 4 to 8, and a couple of other papers, again the paper by Cadelli and Wegner on understanding polymorphism, and a very nice paper by Cook and colleagues on inheritance is not subtyping. Now let's have a look at the different ways that we can understand what subtyping is. Now, first of all, let's take this example of a point where we consider a point being defined recursively with this fixed point operator called mu. Another way of thinking about it, which is essentially equivalent, is that we're taking a fixed point of a generator. So going back to the old lambda calculus, if we wanted to define this recursive function, we would have first defined a lambda which abstracts from self, and then we take a fixed point of it to bind self. So using, for example, the magical Y combinator. This recursively applies the generator to itself. So here we have the abstraction. Here self is simply a lambda, it's an argument, but we need to somehow recursively bind it, so we can do that with a fixed point operator. This is essentially what mu is doing as a built-in predefined operator. The reason I'm abstracting away is because the notion of a generator is going to be extremely important for us to help us understand what classes are as opposed to types. And we see that fundamentally classes and types are not the same thing. In particular, a class serves two purposes. A class is used on the one hand as a stand-in for a type, but it's also used as a generator, which will allow us to create instances, but also to define subclasses. So a class is definitely more than just a type. Now the point as a type must also be recursive, and that's kind of tricky. So point is going to be a fixed point here. So here we can see that. Point is essentially going to be a record, but this record makes use of point itself in its own definition. So we need to take a fixed point. So that's why the type sigma here is a parameter to the fixed point operator, because we want equality to also be defined for points. So we somehow have to deal with this recursion. So that's kind of clumsy. So in other words, we can see that as kind of a shortcut again for a generator here. So here we have an ordinary lambda instead of a mu. So we abstract from sigma. So now it's an argument. And then we take a fixed point of this generator. The real question, however, is what does subtyping mean for such types? So once you have this additional parameter which is recursively bound, is that going to completely mess up the whole story of types? And as we'll see, it does. It makes things extremely messy, and that's the reason why in languages like Java, they have extremely simplified type rules just to get around this hairy issue. Now, there are different ways of thinking about types, as we saw. One really very attractive and simple way of thinking of types is as sets. The type integer is simply the set of all integers. So notice we have the little grid here, and we have the, we're in the center of the grid that we saw earlier. So to say that little x is of type big X is the same as saying that x is a member of the set big X. And to say that big Y is a subtype of big X is the same as saying big Y is a subset of the type X. So, for example, if we say that John is a student and John is also a person, that's because John, as an instance, is a member of the set of students, and the set of all students is a subset of the set of all persons. Looks perfectly reasonable. What's wrong with that notion of types? Types as sets. This is very intuitive and appealing, but it will lead to some problems, as we will see. Okay, let's look at functions and subtyping. So suppose we have a function f of x, f sub x, and it takes instances from the domain dx and maps them to the range cx. Now the question is, when can I safely substitute another function, fy, which maps from dy to cy, when can I safely substitute it for f of x, f sub x, okay? When are they completely compatible? When is this a subtype of that? In other words, what are the relationships that may hold between these sets? Okay, so let's try and draw a Venn diagram to see if we can make sense of this. So Venn diagrams are good for reasoning about sets. So fx is mapping from the set dx to the set cx. Pretty good. So it'll take an element from the one and map it as an element of the other. Pretty good. Now, covariant types say that fy is going to be a subtype if dy is a subset of dx and cy is a subset of cx. So we could draw it like that. Looks pretty reasonable. However, we want these guys to be completely substitutable, right? So this mapping works. Now, here's the question. What happens if we take a value that's in dx that's not in dy? Well, it's completely undefined what fy will do for it. So whereas before we had fx and it was nicely mapping that value to cx, now if we substitute for it fy, it suddenly no longer works for those values. So as a consequence, a client who expects the behavior of fx and applies fy to a value in dx that's not in dy is going to get a runtime type error. So on the one hand, this seems pretty reasonable as a model, but when we look at the details, this causes problems. So interestingly, Eiffel, the programming language Eiffel, adopts covariant types because for a lot of applications that's what you want, but it adds an additional runtime check for these values that are outside of the range of fy. And it will catch these errors at runtime. So this is kind of strange. So covariant types seem reasonable, but they are actually unsound. So a type system is unsound if it says that the types are okay, but at runtime you might still get a type error. So that actually is something kind of wrong. Here's an example of covariant type errors. So this is a bit of Smalltalk code. Here I have a class called myPoint, and it has instance variables x and y, and getters x and y. Getter x returns x, getter y returns y. The caret here is the return symbol in Smalltalk. And it has an equality method. This is not the way you would normally define equality in Smalltalk, as we'll see it has a severe shortcoming. But here, this equality is expecting a point object as an argument. And it just checks, does my x equal to the arguments x, and my y is the same as the arguments y. That's what we expect. That's okay. HotPoint is a subclass of myPoint, and it has an additional instant variable on, which can be toggled, so it can be on or not on. Okay, so we can toggle the on variable, and a HotPoint is equal to another HotPoint if the super method passes, so x equals x and y equals y, and the toggle value is the same. If I have two instances of myPoint and I compare them, two different instances, the value comes out as false. That's fine, what I expect. If I have two HotPoints that are equal and compare them, it comes out true. If I compare a point to a HotPoint, then they're going to be equal because we're just ignoring the toggle value. So as point values, they're okay. But if I compare a HotPoint to myPoint, then I have a problem. Suddenly I get a runtime error. So why is this happening? The reason is that the HotPoint equality method is going to take as an argument a point which is not a HotPoint, and when I invoke the on method, well, this instance doesn't have an on method, so I'll get a runtime error. So this is kind of catastrophic. Notice that in real Smalltalk code you would never implement an equality method like this, and this is the reason why. What you should do instead is the equality method should always take as an argument an arbitrary object. If that object is not the same type as me, I will always return false. Now let's look at contravariant types. This, at first glance, seems much more reasonable than the covariant types because they're going to be sound. So as before, fx maps dx to cx, and fy maps dy to cy, and now our constraint is that instead of dy being a subtype of dx, we reverse it. So instead of being covariant, it's contravariant. So we have a typing rule where the domain should be a supertype and the range can be a subtype. So then we have a type system that's sound and that guarantees that the client will receive no unexpected results. And this is what a contravariant type rule would look like. So it would say that if dx is a subtype of dy and cy is a subtype of cx, then dy arrow cy, that's the type of our fy, is going to be a subtype of this guy, and it's going to be substitutable. So it's substitutable and it's sound. That looks actually pretty reasonable, although in practice it's not very useful. Now let's look at a final case, which is overloading, which seems to help but has other problems. Here with overloading, we have a function fx and we have a function fy, and in fact in many languages like Java and C++, fx and fy, they have different types, they have different argument types, so in fact they're overloaded. So now what we should do is, if we're applying a function f to an argument, if it happens to fall in the range of dy, then we could apply this function, and if it's outside the range, so here, we'll simply apply the old one. So we actually have two functions. We're overloading them. And now all these problems seem to go away. It looks better, doesn't it? So the old and the new methods coexist. You have no type errors, but the domains overlap. And as it turns out, this leads to some other problems. Here's another example. Here we have in Java a point class. Pretty much as we had before. We have our internal representation, we have a constructor, we have our two getters, we have our equality method. Pretty much as we had before. Now we have a hot point, it extends, and it also has an equality method. Notice that this equality method expects a point as an argument, and this one expects a hot point as an argument. It's going to do the super equality and compare the get on Boolean value. Now we have a main, and the main does the following. We create two hot points, they're equal, and we toggle one of them, and now we're going to compare. So now our comparison is going to take these 2 points, compare them, and say whether they're equal or not. Maybe you already see what the problem is. And it says hot point 1 is the same as hot point 2. So clearly something went wrong. As you may have noticed, the problem is here. We have the compare method expects 2 arguments of type point. So the static type of these guys is going to be of type point, and within this scope here, the hot point code is not seen at all. The comparison is going to be resolved to the comparison from the point class and not this one. As a consequence, this comparison is going to be performed and the additional behavior is going to be ignored. So this is one of the things that can go wrong. The type system depends on the static, not the dynamic types. If the dynamic and static types are the same, everything is going okay, but if accidentally something passes into a scope where the dynamic type is lost, then you will not get the behavior that you expect. So the static point is used to select the sen, namely equals from the point class. And this is different from the equals of the hot point, which is only visible in the subclass. There are 2 different equals method and the wrong thing happens. If, on the other hand, we could override rather than overload, then instead we're going to have runtime type errors. So this is what in Eiffel is known as so-called cat calls. And then you have to do some runtime type checks. Okay, so we've seen that covariance and contravariance, all of them, and overloading, they all seem to have some advantages, but in all cases something nasty can go wrong. It's not quite what we wanted. And now let's have a look at how we can specify these different kinds of subtyping rules. First of all, let's consider record extension. This is the kind of rule that you see typically in Java. So Java would say that one record with more fields can be safely substituted for one with fewer fields. But we don't have any covariant or contravariant rules. Instead, we insist that all of these types, T1 through TK, are exactly the same as the ones we find here in the subtype, and then we may have additional ones. So if the types match exactly, then we don't have any of the problems with co- or contravariance or with overloading. All of those issues are put to the side. Everything is sound, it's nice, but you don't have any subtyping on arguments or return types. So this works. Sometimes it's not very convenient, so it's not right for what you want to program. And then if you want to change the types, you're going to get overloading, and that can bring you some other problems. But this is perfectly fine as a rule. We can also have a rule for overriding. So here, for example, we have a bunch of labels as we had before, and we have a bunch of types, SI to TI, which are subtypes. So this is going to be a kind of a covariant rule. So usually most programming languages do not support this. So Java does not, and C++ does not. Eiffel does do it, but the rule is not sound, as we saw. And then you have to do some runtime checks. So typically what we want is some kind of specialization, not subtyping. So in practice, it doesn't seem to be terribly useful. Then, an even more advanced rule is the combination of the two, which will allow you to extend and subtype. But again, it's not clear how useful this would really be. Even more advanced is if you want to have recursive subtypes. This gets kind of nasty. So this was a rule that was proposed by Cardelli here. And if you look at it superficially, it seems to kind of make sense. So here, if knowing that sigma is a subtype of tau, and knowing that would allow you to conclude that S is a subtype of T, then if you recursively bind, so this is a variable, so sigma and T are types that appear in the types S and T. If you then recursively bind these, then these guys should be subtypes. So if knowing that sigma is a subtype of tau lets you conclude that S is a subtype of T, then the recursive type S is a subtype of the recursive type T. Looks superficially kind of reasonable, but does it work in practice? Think back of the number types that we had in Haskell. Remember, integer is kind of a refinement of number. So number was kind of a generic type, and integer was a kind of a number, and so on. So here, then, the question would be, would this allow you to conclude that integer is a subtype of number? Remember, on the other hand, that Haskell doesn't have subtypes. Haskell has parametric polymorphism, but no inclusion polymorphism. So maybe you think that this would work, but maybe there's some problems. Looks okay, but in practice, people keep things much simpler. So in Smalltalk, dynamically typed, you have overriding. Subclasses could disable or restrict inherited methods. C++ and Java, there we have overriding and overloading, which can lead to some weird things, as in the code example we saw, where we could actually break the behavior of some methods because of the static downcasting. We have exact type matching for overridden methods, so it's a much simpler type rule, which is sound, but you can do some dynamic downcasts. And then we have Eiffel, which goes for the covariant type rule, but has runtime type checks, these so-called cat calls, or change in availability of type. Okay, where is this all leading? As we'll see, a lot of the problems are coming from a confusion between what's a class and what's a type. So let's see if we can sort this mess out and come up with a better way of understanding what classes and types are, and subclasses and subtypes. Let's consider again the story of recursive closure. So we have this notion that an object is a closure, like in JavaScript. So in JavaScript we have a hidden part, which is part of the closure, and the object is just a record. And the record may refer to some hidden part that's part of the closure. we can take the same approach with types. So consider the type of an animal. So an animal has a whole bunch of different methods, and it also has a mating method. So two animals can mate and produce another animal. Okay? And since the mate method refers to the animal type, we need to bind it recursively. So animal is recursively bound sigma, so it's this whole guy, and the sigma refers to the whole thing, so animal. So this sigma and that sigma is going to be animal. So the type of animal.mate is going to be from animal to animal. But now, what about dogs and cats? So we want dogs only to mate with dogs and cats only to mate with cats, right? So this is covariance rule, but that's not what subtyping would give us. We saw that covariance is problematic. So let's see if we can enforce subtyping. So if we enforce subtyping, then like in Java, we would say, well, we can't change the type of the argument. We want it to be the same as animal. But then the type of dog.mate would be a dog could mate with an animal and produce a dog, and that's completely wrong. So it's not giving us what we really want. So there's something funny going on here. We want to do some subclassing that would be reasonable, but we also want a reasonable type system. Let's look at a slightly different example. So back to numbers. Here we have a number class which has a bunch of operators, and particularly it has a plus operator from numbers to numbers. And that's recursively bound. So number is mu of sigma, and plus will take a sigma and give us a sigma. So we can add this, and because it's recursively bound, that's the same as number. Okay? And then integer is going to be a subclass, so we want to add some new stuff in. So we're going to add a minus operator, which also does maps from sigma to sigma, and other things as well. Now, if we recursively bind that, mixing in this new method, minus will map from integer to integer, but the old thing we got from number was from number to number. Well, that's not right either. So if we add a j to I, then we're going to get a number back, and then if we want to subtract, well, that won't work because there is no minus defined for numbers. So that's completely wrong. So the point is we're thinking the wrong way about classes, because we're making a class also be a type at the same time, but they're not the same thing. And this is the key point. So class serves two purposes. It's being forced to behave like a type for the type system, but it serves another purpose. It generates instances, and it also is used to generate subclasses. So what a class is really is not a type. A class is a generator of types. Now look at this weird stuff. Now we've seen lots of lambda stuff. Maybe we can make a bit more sense of it now. So if we have, instead of number, think of gen number. So this is going to be a generator for classes. And it takes as a parameter some sigma. It's an ordinary lambda. We haven't taken any fixed point yet. If we take gen number and plug in number, which is going to be a certain kind of a fixed point, then we'll get this guy. If we plug in integer, however, then the sigmas are just going to be bound to integer rather than to number. And if we plug in a complex, then we'll get plus working with complex numbers. That sounds much better. But that's not subtyping, that's generation. So what about subtyping now? Integer is not a subtype of number, because they're not plug compatible. But integer is a subtype of gen number of integer. So when we plug this in, the integer class that we get it's definitely going to be compatible with this guy because they're the same arguments. So we're doing things at different times. This is where the notion of f-bounded quantification comes in. And all this means, so this is from the paper by Canning and colleagues in Uppsala 1989, some time back, and they clarified this whole issue. So what are the types of the number class? Number class actually generates lots of different types. So it's basically all the types that you can plug in here into gen number, and those will give you different types. And all of the ones, so this is saying that the class of number represents a family of types which are subtypes of gen number applied to themselves. Okay, let's see in an example if we can make sense of this. And now we should be able to see that, that classes are not the same as types, but they're actually generators. They represent families of types. So animals and dogs again, we have gen animal, and gen animal is an ordinary lambda. It'll generate a type with a mate method, okay? And the types are parameter here. So for all types tau, whatever they be, gen animal, if we look at its mate method, it's going to be compatible with tau arrow tau. It's going to have that type. So as a consequence, a dog is going to be a subtype of gen animal of dog, because gen animal of dog will have a mate method that allows dogs to mate, but not animals to mate, because we're plugging dog in here. But dog is not a subtype of animal. It's a subclass, not a subtype. Finally, if we see it in this picture, this is a graphical representation of what types and classes are. So what's a type? A type is just a little point, a specific type. And when we refer to the number type, we're fixing all of the type parameters in all of the methods. We're fixing the interface. But number is also a class. And as a class, it represents all of the subclasses that can be defined. And not all of the subclasses are going to be subtypes of the type number. If we have the class integer, which is derived from number as a subclass, it's going to represent a smaller family of types that is contained within the family of types of number. And when we consider integer as a type rather than as a class, it's going to represent a specific type at that point. Considering inheritance then, here we have subclassing without subtyping. Here's a gen number as before. We have a generator. We don't take the fixed point yet. And here we have a generator for integers. So the generator for integers is going to subclass by taking the generator that we had before. Here we see it again. And we have a new sigma that's plugged in here into our generator, and we unify, we add in some additional methods. So this is what's going on in subclassing. We take our parent, we use it as a template, but it's open. It's not fixed yet. We add in some new, we can add in some new methods, self and super, our rebound, and then when we take the fixed point of that, then we actually get a concrete class from which we have instance, we have a type. So this is where we can see the difference between subclassing and subtyping. So if you followed all of that, what do we have as the answers to the questions we saw at the beginning? First of all, what's an object? Well, we saw a bunch of different solutions. The most satisfying one is to think of an object as a functional closure, exactly as we saw in JavaScript. What's a type? Well, a type is a specification of component compatibility, and different programming languages offer different forms of compatibility. some with advantages and disadvantages. So some languages, for example, provide a covariant type system for the subtypes like Eiffel, and others require some more exact matching. So subtype instance can be safely substituted where its supertype is expected, with some caveats. So in an unsound type system, you may need to do some additional runtime type checks. For example, if you have a covariant type system. What's the difference between a class and a type? Well, type is purely used for the type checking. A class, in addition, is a generator both of instances and of subclasses. So you can think of a class as being a family of types. What's the difference between inheritance and subtyping? Well, subtyping, as we saw before, is purely about the substitutability, whereas inheritance is about creating new classes. So it extends a class to give you a new family of types. And when our subclasses also subtypes, we wish that would always be the case, but as we see, we have, with any possible typing scheme that we have, this leads to problems. So in general, it only works if record extension and the contravariant subtyping rules are obeyed. But of course, with all of the mechanisms we have in various programming languages, we can get into some funny situations. So things that we would like to be subtypes are not allowed to be because we restrict the type system, or because we add funny features like overloading with downcasting. We may also violate our type systems and not get the behavior we always expect. So in many cases, subclasses and subtypes correspond exactly, but the moment we start doing interesting things with recursive behavior, then things may start to break down and we may not get precisely the behavior we expect. Okay, thanks very much for your attention. This brings then to a conclusion our foray into the question of what are objects, classes, and types. Thanks for your attention.